In 2004, NASA's WMAP satellite finished painting the most detailed portrait of the early universe anyone had ever seen. The first thing astronomers noticed when they looked at it was that something was wrong. The satellite had spent more than a year sweeping the entire sky. Its mission was precise. Scientists wanted a map, a complete, full sky map of the faintest light in the universe, not the light from stars, not from galaxies, something older, something that had been traveling toward us since before any of those things existed. The cosmic microwave background, the afterglow of the Big Bang itself, a faint wash of microwave radiation arriving from every direction, carrying information about what the universe looked like 380,000 years after it was born. WMAP was built to read that information with a level of detail no instrument had ever achieved before. What came back from the satellite exceeded expectations. The map was extraordinary. Tens of millions of pixels, each one a temperature mirror, shimmered from a different patch of sky. Averaged across the whole thing, the temperature was 2.725 Kelvin, just barely above absolute zero, and the tiny variations scattered across that map, hot patches, cold patches, each one a fraction of a degree from the average, matched the predictions of standard cosmology almost perfectly, almost. There was a region, a broad, irregular patch of sky sitting in the direction of the constellation Eridanus, in the southern part of the celestial sphere. In that region, the temperature was lower, not dramatically lower in the way you might imagine, not something that leapt off the screen in the first glance. The difference was 70 microkelvin, 70 millionths of a degree below the average temperature of the surrounding sky. Written out as a number, it barely registers. 70 millionths. You could be forgiven for wondering why anyone cared. Here is why anyone cared. The CMB is almost perfectly smooth. The variations that do exist across the entire map average around 18 microkelvin. Small fluctuations above, small fluctuations below. These tiny ripples are not noise or imperfection. They are the seeds of every structure in the universe, the slight overdensities that eventually became galaxy clusters, the underdensities that eventually became the vast empty regions between them. The whole story of cosmic structure is written in those tiny temperature differences. And they are small. They are supposed to be small. The universe, at the moment that ancient light was released, was remarkably uniform. So when something appears in the map that is 70 microkelvin below average, nearly 4 times the typical variation, it does not bless. End in. It stands out. Hard. The first question scientists asked was simple. Was it real? Instruments have artifacts. Satellites have noise. Data has errors. Every major discovery in astronomy demands the same first round of scrutiny. Could this be a mistake? Teams went back through the WMAP data. They checked calibration. They ran the analysis again with different techniques. They looked for any systematic error in the satellite's measurements that might produce a cold patch in that part of the sky. Nothing. The cold region held. It was not a glitch in the detector. It was not a processing artifact. It was not a foreground source, some intervening object between us and the CMB that might have contaminated the signal. Every standard explanation for instrumental or observational error came up empty. Whatever this feature was, it was in the data, and it was not going away. Then came the second question. How big was it? This was where things became genuinely uncomfortable. The cold patch covered a region of sky roughly 5 degrees across. 5 degrees sounds abstract. Hold your hand at arm's length and spread your fingers as wide as they go. That span across the sky is about 10 degrees. The cold spot covered roughly half that. Enormous by the standards of CMB anomalies. The area it occupied on the sky corresponded, at cosmological distances, to a physical region of staggering actual scale. Whatever was behind that patch of sky, whatever was causing this temperature dip, if something was causing it, it was not small. This was not a local effect from some nearby structure. The numbers pointed towards something vast, something sitting at a distance measured in hundreds of millions or billions of light years. Cosmologists ran probability calculations. They asked, in a universe governed by the standard model of cosmology, with its well-tested predictions for how temperature fluctuations are distributed across the CMB, how likely was a feature like this to appear by chance? The answers varied depending on assumptions, but none of them were comfortable. Some estimates placed the odds at 1 in several hundred, others were more alarming. Whatever precise number you accepted, the cold spot sat far out in the tail of any reasonable distribution. It was not the kind of feature you expected to find once in the observable universe. The years following that first map brought more scrutiny, not less. Additionally, studies confirmed the anomaly. A second satellite, the European Space Agency's Planck mission, would eventually map the CMB with even greater resolution. The cold spot would still be there, refined and confirmed, its edges better characterized, its depth better measured. Every tool that looked at it saw the same thing. A cold region, roughly circular, sitting in the direction of Eridanus. No obvious cause. No clean explanation from the standard playbook of cosmological physics. The cold spot was real, it was enormous, and nobody had any idea what made it. To understand why astronomers lost sleep over a cold patch in a microwave map, you have to understand what the map actually shows. Roughly 13.8 billion years ago, the universe began in a state of almost unimaginable heat and density. Everything that now exists, every galaxy, every star, every atom in every planet, was compressed into a space smaller than a single proton. In that first fraction of a second, the universe was so hot that light could not travel. Photons would collide almost immediately with the dense fog of plasma surrounding them, scatter, and go nowhere. The universe was opaque, not dark exactly, more like a wall in every direction. This continued for a very long time, 380,000 years to be precise. Then something changed. The universe had been expanding since the moment of its birth, and that expansion meant cooling. When the temperature finally dropped to roughly 3000 Kelvin, about the surface temperature of a dim red star, something critical happened. Protons and electrons, which had been careening through the plasma as separate particles, were able to combine for the first time into stable hydrogen atoms. The fog cleared. Light was suddenly free to travel, and it has been traveling ever since. That light is still out there. Right now, from every direction in the sky, ancient photons released at that moment 13.8 billion years ago are streaming toward Earth and through your walls and across your body without stopping. We call it the cosmic microwave background, the CMB. It is the oldest light in the universe, a relic of the moment the cosmos first became transparent, stretched over billions of years of expansion into the microwave range of the spectrum. It arrives from every direction equally, which tells you something profound. The moment it was released surrounded us on all sides. We are, in a meaningful sense, sitting inside it. When astronomers say the CMB has a temperature of 2.725 Kelvin, they mean the photons arriving at our detectors carry energy consistent with that temperature. 2.725 Kelvin is 270 degrees below the freezing point of water. It is almost absolute zero. The universe, in its old age, runs cold. What makes this number remarkable is not how small it is, but how consistent it is. Point a microwave detector at any patch of sky, and the reading comes back to 2.725 Kelvin. Point it somewhere else. Same answer. The CMB is the most uniform natural signal ever measured by any instrument in the history of science. 1 part in 100,000. That is the scale of the variations that exist. You would need to measure the temperature to 4 decimal places before you would notice anything different from one region to the next. Those differences, though, are everything. The tiny temperature variations embedded in the CMB, fluctuations measured in millionths of a degree, in units called microkelvins, are the fossils of the earliest structure in the universe. Before light was released, the plasma filling the cosmos was not perfectly smooth. There were regions slightly denser than average, regions slightly less dense. Those density differences created pressure waves, rippling through the plasma the way sound waves move through air. When the light broke free, it carried the imprint of those waves with it. Denser regions were slightly hotter, less dense regions were slightly cooler. The temperature map of the CMB is therefore a direct photograph of the state of the universe 380,000 years after its birth, a baby photo, taken before a single star had formed. Those early overdensities are where everything began. Gravity pulled more matter toward the dense spots. Over hundreds of millions of years, that matter collapsed into the first stars. Stars clustered into the first galaxies. Galaxies assembled into clusters and filaments, and the universe began to look the way it looks today. Every structure you see in the night sky traces back, in a direct causal chain, to those tiny temperature variations in the CMB. This is not a metaphor. The positions of galaxies billions of light years away were determined by fluctuations in a 380,000-year-old plasma. The CMB map is the blueprint from which everything was built. This is why cosmologists care so much about getting that map right. It is why WMAP and Planck exist. It is why researchers have spent decades refining instruments capable of measuring temperature differences 1,000 times smaller than anything a laboratory thermometer could detect. Every feature in that map carries information about the conditions of the early universe. What it was made of, how fast it was expanding, what forces were acting on it. The map is a diagnostic tool of extraordinary precision, and the standard cosmological model predicts its features with matching precision. When observation and prediction agree, you gain confidence the model is correct. When they diverge, something is wrong somewhere, which brings you back to the cold spot. In a map where the typical temperature variation from one region to another runs around 18 microkelvin, a feature sitting at 70 microkelvin below average is not a rounding error. It is not instrument noise. It is not something the beam pattern of the satellite smeared into existence. It is a genuine, persistent, enormous deviation from what the standard picture says should be there. The CMB is supposed to look roughly the same everywhere, shaped by those primordial fluctuations into a pattern the model can predict and reproduce. A cold spot that large and that cold had no place in the picture. The numbers, when you actually sit with them, are the part that made cosmologists uneasy. Start with the temperature. The cosmic microwave background is not perfectly uniform. It has variations, tiny wrinkles baked in from the earliest moments of existence. Those variations average around 18 microkelvin above or below the mean. 18 millionths of a degree. That is already almost nothing by any human standard of measurement. The cold spot clocks in at 70 microkelvin below average, nearly 4 times the typical fluctuation. When you are working in a regime where 18 microkelvin is the normal range of variation, 70 microkelvin is not a mild outlier. It is not a rounding error. It is not the kind of number that appears in your data and gets quietly set aside. It is the kind of number that stops a room. Now consider the size. The cold spot spans roughly 5 degrees across the sky. That sounds modest. 5 degrees is about 10 times the width of a full moon as seen from Earth. But the CMB is not a nearby surface. The light making up that map left its source when the universe was only 380,000 years old, and it has been traveling toward us ever since across a distance of roughly 46 billion light-years. At that range, 5 degrees of arc translates into a physical region of staggering scale. The cold spot, projected back to where it originated, covers a patch of the early universe several hundred million light-years across. This is not a blemish. This is a continent-sized wound on the map of everything. Hold those two facts together. Colder than it should be by nearly 4 times the typical variation, and enormous. Not a pinpoint. Not an artifact of a single bad detector reading. A vast, coherent, anomalously cold region sitting in the same part of the sky every time anyone looks. The Planck satellite looked. WMAP looked before it. Both found the same thing in the same place. The cold spot does not go away. Here is where the statistics enter and where things get genuinely uncomfortable for anyone doing the math. The Lambda-CDM model, the standard cosmological framework, makes specific predictions about what the CMB should look like. It predicts the distribution of temperature fluctuations across the sky with extraordinary precision. Most of the sky matches those predictions beautifully. Then there is Eridanus. Researchers ran the numbers on how likely it would be within a standard Lambda-CDM universe to find a feature this cold and this large appearing by chance. The answers depend on the statistical method and how you define the question, which is itself part of the problem. But the range of answers is telling. Some analyses put the probability of this feature occurring randomly at around 1 in 50. Others, using tighter definitions or different statistical frameworks, calculated odds closer to 1 in several thousand. 1 in 50 is uncomfortable. 1 in several thousand is the kind of number that, in a different field, would end a debate. The fact that the range spans such a wide interval is not evidence that the cold spot is unimportant. It is evidence that the statistics are genuinely hard, and that serious people working carefully with the same data are arriving at very different conclusions about how alarmed to be. What everyone agrees on is that the cold spot sits at the extreme tail of the distribution. Whatever probability you assign it, it does not live near the center of what the standard model expects. It lives out at the edge, in territory the model visits rarely if at all. There is a specific way that astronomers talk about statistical outliers. They use sigma, the measure of how many standard deviations a measurement sits from the expected mean. A 1 sigma outlier is common. 2 sigma, you start paying attention. 3 sigma is enough to publish a paper. 5 sigma is the threshold particle physicists use to declare a discovery. The cold spot sits somewhere in the range of 3 to 4 sigma, depending on whose analysis you trust. That is not a flicker. That is a signal. Some researchers argued early on that the cold spot might be a selection effect. When you examine a full sky map and go looking for the single coldest region, you are by definition going to find the coldest region. The act of selecting the most extreme feature and then asking how extreme it is can inflate the apparent significance of any anomaly. This is known as the look elsewhere effect, and it is a legitimate methodological concern. Cosmologists took it seriously. They corrected for it. The cold spot remained anomalous after the correction, not as dramatically in some analyses, but it survived. It kept surviving. Then there is the question of its shape. A random thermal fluctuation tends to look like noise, irregular, without clean internal structure. The cold spot has a measurable profile. It has a colder core surrounded by a slightly warmer ring, which in turn sits inside the broader cold region. That kind of internal organization is unusual. It suggests the feature has physical coherence rather than being a random collection of unrelated temperature dips that happen to cluster together. A truly random fluctuation does not generally come with architecture. By the mid-2000s, The cold spot had survived every attempt to make it disappear. It survived instrument checks. It survived reanalysis with better data. It survived statistical corrections designed to reduce its apparent significance. It kept standing there in the Eridanus region of the sky, colder than it should be, larger than the models could comfortably produce, shaped in a way that random chance could not easily explain. Whatever was causing the cold spot, it was not going to be something small. Matter in the universe does not spread evenly and never has. From the very first moments after the Big Bang, tiny fluctuations in density were already written into the fabric of space. Some regions had slightly more matter than others. Gravity did the rest. Over hundreds of millions of years, matter began flowing. It drained away from underdense regions and piled up in denser ones. The process accelerated. Dense regions became denser. Empty regions became emptier. What you are left with, after 13.8 billion years of this, is not a smooth universe at all. It is something that looks almost biological when you map it at large enough scales. A vast three-dimensional web of filaments and walls and clusters, threaded through with enormous hollows where almost nothing lives. Cosmologists call this the cosmic web. The name is apt. The bright nodes where filaments intersect are galaxy clusters, the most massive gravitationally bound structures in the universe. The filaments themselves are long chains of galaxies in gas, some stretching for hundreds of millions of light years, connecting cluster to cluster like strands under tension. Between the filaments are sheets, flattened walls of galaxies thinner than the structures they bound. And between all of it, filling the spaces left behind when matter abandoned them, are the voids. Not holes in the ordinary sense, not walls of emptiness with sharp edges. Voids are softer than that. They are regions where the density of matter falls well below the cosmic average, sometimes dramatically so, and where galaxy formation simply never got a strong foothold. The surprising thing, when you work out the numbers, is how much of the universe these voids actually account for. Depending on how you define the boundaries, voids fill something close to 70% of the total volume of the observable universe. 70%. Most of the space that exists is space where almost nothing is. The galaxies, the stars, the clusters, all the light we have ever detected. That is confined to roughly a third of the universe's volume, pressed into the web's filaments and walls like foam on the surface of something enormous and dark. The voids are not the exception, they are the rule. This was not obvious until 1981, when a team of 4 astronomers, Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman, published a survey of galaxy positions in the direction of the constellation Boötes. What they found stopped the field. Where they expected to see a more or less continuous distribution of galaxies, thinning gradually with distance, there was instead a nearly empty region roughly 250 million light-years across. Almost no galaxies, just space. The Boötes void, as it came to be called, became one of the most studied features in large-scale structure research. It was the first clear demonstration that the universe's emptiness had structure, that voids were not random noise, but genuine features, carved out by the same gravitational processes that built the web itself. 250 million light-years is not a small number. If you could travel at the speed of light, crossing the Boötes void would take longer than the Earth has existed. Yet it sits in the universe the way a single bubble sits in a larger foam. The cosmic web contains many such voids, most of them discovered after the techniques for finding them improved. Redshift surveys, which measure the distance to galaxies by stretching of their light, made it possible to build 3-dimensional maps of the galaxy distribution across billions of light-years. Those maps kept showing the same pattern: filaments, clusters, walls, and everywhere between them, the voids. Most voids are unremarkable in isolation, a few 100 million light-years across, underdense but not empty, containing scattered galaxies at lower than average density. Then there are the ones at the extreme end of the distribution, the ones astronomers call supervoids. A supervoid is not simply a large void. It is a structure where the underdensity is deep, where the volume is vast enough to be measured not in hundreds of millions of light years, but in billions, and where the matter deficit is so severe that the region stands apart from the rest of the cosmic web, the way the Boötis void stood apart from everything astronomers had seen before it. Supervoids are rare. The conditions needed to produce them, sustained outflow of matter over billions of years, in a region that started off unusually underdense, make them statistical outliers even in a universe full of voids. Understanding why supervoids matter for the cold spot problem requires one more piece of physics, which will get its own full treatment in the next section. But the outline is this: the cosmic microwave background photons we detect today did not travel through empty, featureless space to reach us. They traveled through the cosmic web. They passed through clusters and filaments and walls. They also passed through voids. And when a photon travels through a void, through a region where the gravitational environment is weaker than average, a kind of gravitational hill rather than a valley, something happens to its energy. The expansion of the universe plays a role. The interaction is subtle and has a name: the Integrated Sachs-Wolfe Effect. A photon that passes through a deep enough void in an accelerating universe does not emerge from the other side with the same energy it carried going in. The consequence is measurable. In principle, a sufficiently large and deep void, sitting along the line of sight between us and the CMB, would leave a cold imprint on the map. A patch of sky in that direction would read slightly colder than its surroundings. Not because the void itself is cold, but because the photons that passed through it lost something they could not recover. The map would show a depression in temperature, faint but real, centered on the direction of the void. The cold spot in Eridanus is 70 microkelvin colder than average. It spans roughly 5 degrees across the sky. It has no explanation in the standard model that fully accounts for its depth or size. If you could find a supervoid sitting in exactly the right place along the line of sight to the cold spot, you would have the beginning of an answer. There is a mechanism in physics, subtle, quiet, operating across billions of light years, that could connect an empty region of space to a cold patch in the oldest light in the universe. To understand it, you need to hold two things in your mind at once. The first is that light is not immune to gravity. A photon falling into a gravitational well gains energy. It blue ships slightly, arriving at the far side of that well a little hotter than it started. The reverse is also true. A photon climbing out of a gravitational well loses energy. It redshifts. It arrives a little colder. This is not a theoretical curiosity. It is a measured, confirmed prediction of general relativity, and it operates on every photon crossing every structure in the universe. The second thing is that voids are not neutral terrain. A void is not simply empty space. It is a region where matter is absent, and that absence has gravitational consequences. If a dense cluster of galaxies is a valley, a deep well that photons fall into and climb out of, then a void is a hill. A photon approaching a void has to climb that gravitational hill before it can descend the other side. It loses energy on the way up. It should recover that energy on the way down. In a static universe, the climb and the descent would be perfectly symmetrical, and the photon would arrive at our detectors with the same energy it started with. The two effects would cancel exactly, but we do not live in a static universe. The universe is expanding. Dark energy is accelerating that expansion, and this changes everything about how a photon experiences a void. Picture that gravitational hill. A photon begins climbing it, losing energy as it goes. While the photon is crossing the void, the universe continues to expand. The void itself stretches. By the time the photon reaches the far side and begins descending, the hill is not quite the same hill it started climbing. The descent is shallower than the ascent. The photon cannot recover everything it lost on the way up, because the potential well it is descending into has weakened during the crossing. The photon emerges from the void carrying slightly less energy than it carried going in. It is colder. This is the Integrated Sachs-Wolfe effect. The name honors Rainer Sachs and Arthur Wolfe, who worked out the mathematics in 1967, well before it could be tested. The word integrated matters. It is not a single event at a boundary. The effect accumulates across the entire crossing, adding up over hundreds of millions of light years as the photon passes through the gravitational landscape of large-scale structure. Every void the photon traverses, every underdense region along its path, contributes a small deficit of energy, colder by a tiny amount here, colder by a tiny amount there. Think of it this way. Imagine rolling a ball across a landscape of hills and valleys. On flat ground, a hill and a matching valley cancel out. You end up at the same height you started. But now imagine that while the ball is crossing the hill, the ground behind it slowly rises. When the ball reaches the valley on the other side, the valley is shallower than it used to be. The ball loses more height than it gains back. It arrives lower than it began. A photon crossing a void in an expanding universe is that ball. It arrives at our telescopes carrying less energy than it would if the void had not been there. The effect is genuinely small. For a typical void, the temperature deficit imprinted on the CMB is measured in microkelvin, millionths of a degree. You would never detect it from a single photon or even from a small patch of sky. What makes the effect observable is scale. When you look at a very large void, a supervoid, you are looking at a structure that photons spend an enormous amount of time crossing. The crossing might take hundreds of millions of years. Every moment of that crossing, the expansion of the universe is quietly working against the photon's ability to recover what it lost. The energy deficit accumulates. The resulting cold signature, averaged across the angular extent of the supervoid on the sky, becomes something measurable. This is how a cold spot could appear in the CMB in the direction of a supervoid. The ancient light from the surface of last scattering, traveling toward us for nearly 14 billion years, passed through the matter landscape of the universe on its way here. Wherever it crossed a dense structure, it blued slightly. Wherever it crossed a void, it reddened slightly. Those tiny temperature shifts are recorded in the microwave map as warm and cold patches overlaid on top of the primordial fluctuations from the Big Bang itself. The ISW effect is a layer of cosmic history written on top of the oldest signal in the universe. Were the ISW effect strong enough, a sufficiently enormous void could leave a temperature depression measurable on the scale of what WMAP detected in Eridanus. That is the connection. That is what makes a supervoid a candidate explanation for a cold patch in the CMB. It is not exotic physics. It is not speculation. It follows directly from general relativity, from the confirmed expansion of the universe, and from the confirmed acceleration driven by dark energy. The only question is whether the void in question is large enough and empty enough to produce the observed effect at the required magnitude. You need the void to be real. You need it to be deep. You need it to span a volume large enough that photons spend a meaningful fraction of their journey crossing it. And you need it to sit at the right distance, close enough that the expanding universe has had time to work on its gravitational potential, but far enough that the CMB photons were genuinely passing through it long ago. A big enough void, in the right place, would leave exactly the kind of cold mark that was sitting in the Eridanus region of the map. In August of 2007, astronomers announced they had found something in the direction of the cold spot that made the whole problem considerably stranger. Not stranger in a way that pointed toward a solution, stranger in a way that raised the stakes. Because what they found sitting behind the cold spot was not a galaxy, not a cluster, not a filament. It was an absence, a region of space so much emptier than anything around it that the word void barely seemed adequate. The search had been methodical. After the cold spot turned up in the WMAP data and survived every attempt to dismiss it as noise or instrument error, a small group of researchers decided to take the ISW hypothesis seriously and look for a physical structure that could be producing the signal. The logic was straightforward. If a supervoid sitting along the line of sight to the cold spot was responsible for cooling those CMB photons, then the supervoid had to be there. It was a testable prediction. You could look. So they looked. What that looking required was a galaxy survey, a systematic measurement of how galaxies were distributed in that patch of sky, at a range of distances. Galaxies are not evenly spread through space. They cluster where matter clusters. Where matter thins out, galaxies thin out with it. If a supervoid was sitting in the direction of Eridanus, the galaxy counts in that direction should drop, and not just slightly. A structure large enough to cool CMB photons by the amount observed would have to be enormous, which meant the galaxy deficit should be hard to miss. Researchers pulled data from existing surveys, ran redshift measurements to establish distances, and began building a three-dimensional map of the matter distribution along that line of sight. Redshift measurements work because the universe is expanding. Light from distant galaxies gets stretched as it travels toward us, shifting toward longer wavelengths. The more distant the galaxy, the greater the shift. By measuring how much a galaxy's light has shifted, you can calculate how far away it is with considerable precision. Stack enough of those measurements together and you get a map, not just of where galaxies appear on the sky, but of where they sit in three-dimensional space, at what distances, in what concentrations. That is the kind of map that reveals voids. The map that emerged from the data pointed at something extraordinary. Out at a distance of roughly 1.9 billion light-years, in the exact direction of the cold spot, the galaxy density fell off a cliff. The deficit was not subtle. Galaxies that should have been there simply were not. The region was not completely empty. A supervoid is not a perfect vacuum, but the number of galaxies present was roughly 30% below what you would expect based on the surrounding cosmic average. That is not a statistical fluctuation. That is a structural feature. As researchers mapped the extent of the underdensity, the scale became harder to hold in your head. The void stretched across roughly 1.8 billion light-years. Its shape was not spherical. It was elongated, extended along one axis more than others. Some researchers described it as cigar-shaped. This asymmetry was itself informative. Matter does not drain away from a void uniformly in all directions. The shape of a void reflects the geometry of the large-scale structure surrounding it. The directions in which matter was preferentially drawn off into neighboring filaments and walls over billions of years of cosmic evolution. The Eridanus Supervoid had been carved out gradually by the slow gravitational tug of everything around it pulling matter away from a region that started out slightly underdense and became vastly more so over cosmic time. To call this one of the largest structures ever identified in the observable universe is not hyperbole. It is simply the accurate description. The observable universe stretches roughly 93 billion light-years across. A single void spanning 1.8 billion light-years of that represents a feature of genuine cosmic significance. For comparison, the Milky Way galaxy is roughly 100,000 light-years across. The Eridanus Supervoid is about 18,000 Milky Ways wide. That number does not help very much. Nothing does, at these scales. What it means, practically, is that a photon of light crossing the supervoid at the speed of light would spend over 1 billion years in transit, just getting from one side to the other, The confirmation carried a specific weight that went beyond the scientific result itself. For 3 years since the cold spot appeared in the WMAP data, the dominant response from the cosmological community had been skepticism and uncertainty. Was this a real feature of the universe or an artifact of the way the data was processed? Was it genuinely anomalous or just an outlier that standard cosmology could accommodate at the tails of its probability distribution? Was there any physical structure in the universe that could account for it? Or was the cold spot pointing at something in the early universe that no structure in the modern one could explain? The Supervoid answered at least one of those questions. There was something there. The galaxy surveys were not ambiguous on this point. The matter deficit was real. It was large, and it was sitting in precisely the right place. Whether it was large enough and deep enough to explain the full temperature depression observed in the cold spot was a separate question, one that required more detailed analysis. But the starting point, the question of whether a candidate physical structure existed, had just gone from open to answered. Here was an underdensity on a scale that had not been catalogued before, sitting behind the single most puzzling feature in the cosmic microwave background map, in a position and at a distance where the ISW effect could plausibly leave a cold imprint in exactly the direction where the cold spot was observed. Coincidences in science are not impossible, but a coincidence of this specificity, this structure, this size, this location, was exactly the kind of thing that makes researchers sit up straighter and start running numbers in earnest. For the first time, the cold spot had a candidate explanation, and it was sitting 1.9 billion light-years away in the form of the largest identified void in the observable universe. The number 1.8 billion light-years is one of those figures that sounds impressive but does not automatically mean anything to the brain that encounters it. So start smaller. The Moon sits roughly 239,000 miles from Earth. Light covers that distance in about 1.3 seconds. When you look up at a full moon, you are seeing light that left its surface a little over a second ago. That gap, 239,000 miles, is the largest distance most humans will ever intuitively feel. It is where our sense of scale begins to break down, push outward. The Sun is 93 million miles away. Light takes 8 minutes to cross that distance. If you replace the Moon with the Sun as your mental measuring stick, you have already multiplied your sense of distance by roughly 400. The nearest star to our own, Proxima Centauri, sits about 4.2 light-years away. Light leaving Proxima tonight will not reach Earth until the year 2029. 4 years of travel at the fastest speed the universe permits. Hold that. A single star, the closest one, takes 4 years of light travel to reach us. The Milky Way is 100,000 light-years across. If you could somehow compress all of human history into the time it takes light to cross our own galaxy, every civilization, every war, every generation of recorded thought, you would not make it past the first fraction of a second. The local group, the cluster of galaxies our Milky Way belongs to, including Andromeda, spans roughly 10 million light-years. That is 100 Milky Ways laid side by side. Now you are ready for 1.8 billion light-years. The Eridanus Supervoid is 1.8 billion light-years across. That is 18,000 Milky Ways. It is 180 local groups. It is a span of space so extreme that the light crossing it takes longer than the entire age of the Earth, longer than the Sun has existed. Our solar system formed about 4.6 billion years ago. Light that entered one edge of the Eridanus Supervoid when our solar system was young and newly formed would still have hundreds of millions of years left to travel before reaching the other side. The entire observable universe, everything we can in principle detect with our instruments, spans roughly 93 billion light-years in diameter. The Eridanus Supervoid represents approximately 2% of that total width. 2% sounds like a small number. Apply it to a structure the size of the observable universe, and it stops sounding small very quickly. What makes the supervoid more than just an enormous empty zone is what is missing inside it. Matter in the universe averages out to a certain background density. The Eridanus Supervoid runs about 30% below that average, not 3%, not a mild underdensity that might blur into statistical noise, 30%. And that 30% figure applies to the overall structure. Toward the center of the void, the deficit deepens. The middle is emptier still, a region where galaxies are not merely scarce, but genuinely profoundly rare. Matter has been draining out of this space for billions of years, flowing outward toward the denser filaments and walls of the cosmic web that surround it. And what is left behind is something close to a gravitational desert. The shape of the supervoid adds another layer of strangeness. It is not a rough sphere, the way you might imagine a bubble or a gap. It is elongated, stretched, something like a cigar extended across space. That shape is a record of how the void formed. Matter did not flow away from this region equally in all directions. It drained preferentially along certain axes, leaving behind an asymmetric absence. The elongated structure tells you that the gravitational landscape around this void was itself uneven, pulling matter harder in some directions than others. The shape is a fossil, frozen evidence of the forces that carved this region out of the cosmic web. For context, consider the Bootes void. Discovered in 1981, it was the first large void astronomers confirmed, and for a long time it served as the standard example of how empty the universe could get in places. The Bootes void is roughly 250 million light-years across. When it was found, that size was stunning. Astronomers struggled to explain how such a large empty region could form within standard models of structure formation. For years it occupied a special place in discussions of cosmic structure, a genuinely exceptional feature. The Eridanus Supervoid is roughly 7 times wider than the Bootes void. 7 times. The structure that once defined the upper boundary of what seemed possible for a cosmic void is dwarfed so completely by the Eridanus Supervoid that the comparison almost becomes difficult to make. If you place the Bootes void inside the Eridanus Supervoid, you would have room for several more like it before you approach the edges. There is a specific kind of unease that comes with processing this properly. The word void suggests something simple, an absence, a gap, a nothing. But what the Eridanus Supervoid actually represents is the cumulative result of billions of years of gravitational dynamics operating across a region of space larger than most of what we can detect with our instruments. Galaxies formed inside it, because even an underdense region produces some structure, but they formed more slowly, more sparsely, more dimly than anywhere else we can identify. The void is not empty in an absolute sense. It is empty in the way that a drought-stricken landscape is empty. Life still holds on, but what should be there mostly isn't. By any measure that makes sense to a human being, the Eridanus Supervoid is not a feature of the universe so much as it is an absence that the universe has been building for billions of years. By 2015, the Dark Energy Survey had accumulated enough data on hundreds of millions of galaxies to settle the question of whether the supervoid was really there. The Dark Energy Survey is not a small instrument. It is one of the most ambitious mapping projects in the history of observational astronomy, a collaboration involving hundreds of scientists across dozens of institutions, using a 570 megapixel camera mounted on a telescope in the Chilean Andes to image roughly 1/8 of the entire sky. Its primary purpose was to understand dark energy by tracking how the large-scale structure of the universe has changed over billions of years. To do that, it needed to map galaxies, hundreds of millions of them. It needed to know where they clustered, where they thinned out, and where they were simply absent. That made it exactly the right tool for the Eridanus problem. The 2007 discovery of the supervoid had been suggestive, convincing even, to many researchers. But the original detection relied on shallower surveys with incomplete coverage of the relevant region. You could see the outline of something large and empty in that direction. What you could not do was measure it with confidence, pin down its true dimensions, its density profile, how deep the matter deficit actually ran. The question of whether the supervoid was genuinely extreme enough to matter, or whether it was a modest underdensity that astronomers had talked themselves into overinterpreting, remained open. That discomfort lived in the literature for nearly 8 years. Then the DES data arrived. Researchers turned the survey's accumulated observations toward the Eridanus region and began counting. Not a rough census. A precise, systematic accounting of galaxy density across that entire patch of sky at multiple distances, using redshift measurements to peel apart the structure in 3 dimensions. What they found removed the ambiguity. The supervoid was there, it was large, and the matter deficit at its core was not modest. The region contained roughly 30% less matter than the surrounding cosmic average, with the underdensity growing more pronounced toward the center. The Eridanus supervoid was not a smudge in noisy data, it was a feature, the most prominent void in the entire DES dataset. That last point deserves a moment. The Dark Energy Survey observed a volume of the universe containing hundreds of millions of galaxies and spanning billions of light years in multiple directions. Within that entire catalogue, researchers identified many voids. Underdense regions are a normal part of the cosmic web. They come in different sizes and depths. When researchers ranked the voids in the DES dataset by how extreme they were, the Eridanus supervoid sat at the top. The largest survey of its kind had found no void anywhere in its field more pronounced than the one sitting behind the cold spot. But galaxy counts alone, while compelling, carry a limitation. Galaxies trace ordinary matter, the stars and gas that emit or block light, and can therefore be detected directly. They do not trace dark matter. And dark matter, which makes up roughly 5 times as much of the universe's total matter budget as ordinary matter does, is invisible to direct observation. A void confirmed through galaxy counts alone is a void confirmed for one component of the universe's matter. The DES team knew this, so they used a second method entirely. Gravitational lensing is the bending of light by mass. Every massive object in the universe distorts the path of light traveling near it, slightly stretching or shearing the images of background sources. In a region that is underdense, where mass is systematically absent, this lensing effect is reduced. Background galaxies behind the void appear less distorted than they would if normal amounts of matter were present. By measuring the shapes of galaxies behind the Eridanus region with great precision and comparing them to what standard distributions would predict, the DS team could directly probe the gravitational environment of the supervoid. They were not counting galaxies, they were weighing the space itself. The lensing signal confirmed what the galaxy counts had shown. The Eridanus region was deficient, not just in ordinary matter, but in dark matter as well. Both components of the universe's matter budget showed the same deficit in the same place. The underdensity was not a quirk of how galaxies had formed in that region, some local suppression of star formation that left the dark matter structure intact. The underlying mass distribution, dark matter and all, was genuinely depleted. The supervoid ran all the way down. This convergence matters. In observational science, 2 independent methods that share no systematic errors and rely on completely different physical phenomena can still occasionally agree by chance. That probability shrinks towards 0 when they agree on a structure of this scale and at this level of precision. The DES confirmation was not merely statistical reassurance, it closed the door on the most credible alternative interpretations. The Eridanus Supervoid was real in the only sense that counts in physics. Multiple distinct lines of evidence, built on different assumptions, using different data, pointed at the same object and measured the same thing. What the 2015 result gave the field was not a solution. The cold spot still sat in the CMB, still colder than anything standard models predicted with ease. The supervoid still sat along the line of sight, now confirmed beyond serious doubt. Whether the one caused the other, and by how much, remained a harder question. But at least the question had graduated from whether the supervoid existed to what it actually meant. That was progress. Two completely independent methods, galaxy counts and gravitational lensing, had pointed at the same vast emptiness in the same direction, and both agreed. The supervoid should have solved the problem. By 2015, astronomers had two things they had been looking for since the cold spot first appeared in the WMAP beta 11 years earlier. They had a real structure in the right place, confirmed by two independent methods. And they had a physical mechanism, the Integrated Sachs-Wolfe effect, that could connect that structure to the temperature depression in the CMB. The pieces were on the table. The case looked like it was closing. Then someone ran the actual numbers. The Eridanus Supervoid, under the standard Lambda-CDM cosmological model, should produce an ISW imprint of roughly 20 microkelvin at its center. That is a meaningful signal. It is not nothing. But the cold spot in the WMAP and Planck data sits about 70 microkelvin below the average temperature of the CMB. Run the arithmetic and you find that the supervoid, vast as it is, can account for somewhere between 10 and 20% of the observed temperature depression. The rest has no explanation sitting behind it, no structure, no mechanism, no name. This is the number that has been bothering cosmologists ever since. It is worth pausing here to understand why this gap is so uncomfortable. The Lambda-CDM model is not a rough sketch of how the universe works. It is one of the most precisely tested frameworks in all of science. It predicts the temperature fluctuations of the CMB across the entire sky with extraordinary accuracy, matching observations at the level of parts per 100,000 almost everywhere you look. When astronomers say the standard model works, they mean it works the way a Swiss watch works, not approximately, not most of the time. Consistently, to a degree that is almost unreasonable, the cold spot does not fit that picture. At 70 microkelvin below average, it sits far outside what the standard model comfortably predicts. The typical variation across the CMB is around 18 microkelvin. The cold spot is nearly 4 times that size, in the wrong direction, in a region that should look more or less like everything else. And now, even after finding the largest identified supervoid in the observable universe sitting directly behind it, researchers can explain at best 1/5 of what they are seeing. The supervoid shifts the problem from completely mysterious to mostly mysterious. That is progress technically. It does not feel like much. The question became urgent precisely because the universe should follow these tested rules at every scale. The standard model had proven itself across countless independent measurements and predictions. A failure of this magnitude suggested something fundamentally unresolved in the current understanding, even if only at the margins of what the model claimed to explain perfectly. Andras Kovacs, one of the lead researchers on the 2015 study, and subsequent work connecting the supervoid to the cold spot, described the situation with the kind of careful precision that scientists use when they want to be honest about what they do not know. Having the coincidence of two individually rare structures, he said, one in the CMB and one in the distribution of matter, is not by itself enough to prove causality to a scientific standard. Two rare things appearing in the same direction in the sky is striking. It compels attention. It invites explanation. But striking is not the same as proven. The supervoid and the cold spot may be related. The physics of the ISW effect says they almost certainly interact. What the math will not support is the claim that the supervoid is the whole answer, because the whole answer requires something 5 to 10 times stronger than the supervoid can deliver. This distinction mattered profoundly to researchers evaluating competing explanations. A complete accounting demanded not merely a supervoid, but one so powerful and so positioned geometrically that it could explain the entire anomaly through physics everyone already understood and accepted. This creates a specific kind of scientific frustration. When an anomaly has no explanation at all, you can at least hold on to the hope that the right structure, the right mechanism, the right observation is still out there waiting. When an anomaly is partially explained, the remaining gap becomes harder to think about clearly. Researchers know the supervoid is real. They know the ISW effect operates. They know those two facts together account for some fraction of what they see, and they are left staring at the rest of the gap, with very few obvious places to look. Some researchers have proposed that the supervoid might be deeper or more extended than current surveys have fully resolved, and that a more complete three-dimensional map of the matter distribution in that region might close the gap somewhat. If the underdensity is steeper toward the center than current measurements suggest, the ISW signal could be stronger than the standard estimates. This is possible. It is also not a comfortable explanation to lean on, because it amounts to saying the data we have is incomplete in exactly the way needed to fix the problem. That kind of reasoning tends to make careful scientists uneasy. Others have pointed to the statistical difficulty of the problem itself. The cold spot is an extreme feature. The supervoid is an extreme structure. Both are rare within the standard model individually. The probability of finding them both in the same direction, even if they have no causal relationship, is not zero. Some researchers have argued that the cold spot may simply be a place where several independent rare fluctuations happened to overlap, producing a temperature depression that looks too large to be explained by any single cause, because it genuinely has more than one cause, none of which is particularly exotic. This explanation is technically allowable. It is also, to put it plainly, unsatisfying. It explains the anomaly by multiplying the number of things that need explaining. What nobody has produced is a mechanism that bridges the remaining gap cleanly, one that uses known physics, fits the confirmed properties of the supervoid, and accounts for the full 70 microkelvin without requiring new assumptions layered on top of old ones. The cold spot arrived in the data in 2004. The supervoid was confirmed in 2015. The ISW calculation was done carefully by multiple groups, using different methods, arriving at the same uncomfortable fraction. A decade of work after the confirmation produced a well-characterized partial explanation and a gap that has not narrowed. The void explained some of the cold spot, but not nearly enough, and whatever was making up the difference had no name in the standard picture. The Lambda-CDM model is the most successful theory in cosmology, and that is precisely what makes the cold spot uncomfortable. Lambda-CDM is the name cosmologists give to the standard framework describing how the universe is built and how it behaves. The lambda stands for dark energy, the mysterious force driving the accelerating expansion of space itself. CDM stands for cold dark matter, the invisible scaffolding around which ordinary matter clumps and organizes. Add in the small fraction of ordinary atoms, electrons, and protons that make up everything you can see or touch, and you have the three ingredients the model uses to construct a universe. What makes this framework remarkable is not its elegance, though physicists find it elegant. What makes it remarkable is how precisely it works. Lambda-CDM predicts the large-scale distribution of galaxies. It predicts the age of the universe, its geometry, its expansion rate. It predicts the temperature fluctuations in the cosmic microwave background, those tiny millionths of a degree ripples across the oldest light in existence. With an accuracy that borders on unsettling, point a satellite at the sky, measure the CMB, and then run the Lambda-CDM equations. The match, across nearly the entire sky, is extraordinary. This is not a model that has survived on theoretical elegance alone. It has survived because the data keeps confirming it. Decades of observations from COBE, WMAP, Planck, and dozens of ground-based experiments have tested Lambda-CDM against the real universe and found it holding. Cosmologists do not trust it out of habit. They trust it because it has earned that trust, measurement by measurement across an enormous range of scales and phenomena, which is exactly why the cold spot creates such discomfort. Not because the model is obviously wrong, but because the cold spot sits in a part of the statistical distribution where Lambda-CDM says features like it should be extraordinarily rare. The model does not forbid the cold spot. That is a crucial distinction. What it says is that a temperature depression this large, this cold, and this spatially coherent should occur by chance only very rarely in a universe like ours. And when a successful model says something should be rare, and then you find it sitting in your data anyway, you have a problem that demands careful handling. The way physicists approach this kind of problem is through statistical analysis. You ask a precise question. Given the universe Lambda-CDM predicts, how often would we expect to see a feature at least as extreme as the cold spot appearing in a random sky map? To answer that, researchers run simulations, thousands of them, sometimes tens of thousands. Each simulation generates a CMB sky consistent with Lambda-CDM's predictions, and researchers scan each one for cold spots comparable to the Eridanus anomaly. The fraction of simulations where a comparable feature appears gives you a probability estimate. Simple in principle, enormously sensitive to the details in practice. Here is where the debate becomes uncomfortable in its own right. Different research groups have run this kind of analysis and arrived at genuinely different answers. Some find that the cold spot is a 1 in 50 event, unusual, worth noting, but not evidence of physics beyond the standard model. Others run the same fundamental test with different assumptions and find the odds closer to 1 in several hundred. A handful of analyses push that number further still, into the range of 1 in a few thousand. The probability estimates span nearly 2 orders of magnitude depending on who is doing the calculation and what choices they make along the way. What drives that spread? Several things. The first is a problem statisticians call the look elsewhere effect. When you examine an entire CMB sky and search for anomalous cold spots anywhere in it, you are essentially running thousands of independent tests simultaneously. Finding one extreme feature somewhere in the data is less surprising than finding it at a specific predetermined location. How you correct for searching the whole sky at once significantly changes your final probability estimate. Researchers disagree, sometimes sharply, about the right correction to apply. The second complication is the choice of what exactly you are measuring. A cold spot can be characterized by its minimum temperature, its average temperature across its area, its total angular size, the sharpness of its edges, or combinations of all of these. Different statistics capture different aspects of the feature, and different groups have used different statistics, sometimes producing meaningfully different assessments of how anomalous the cold spot is. The third problem is deeper and harder to resolve. Lambda-CDM itself has 3 parameters, numbers that are measured from the data and then fed into the model. When you use the same dataset to both calibrate the model and test whether an anomaly is consistent with it, the statistics become entangled in ways that are genuinely difficult to untangle. Some critics of the cold spot's claimed significance argue that the model has already been adjusted implicitly to accommodate the universe we observe, and that tests of rare features using that same calibrated model understate their true improbability. This is not a fringe concern. It is a legitimate methodological worry that careful cosmologists take seriously. What this means in practice is that no single probability number attached to the cold spot should be taken at face value without understanding the assumptions behind it. When a headline says the cold spot has a 1 in 50 chance of occurring randomly, that is one answer to one specific question asked in one specific way. It is not the whole picture. The honest assessment is that the cold spot is unusual enough that many independent researchers, using different methods, keep flagging it as something worth explaining, while simultaneously being just ambiguous enough statistically that no one can declare with finality that the standard model is broken. That ambiguity has persisted for 20 years. The data have gotten better, the simulations have become more sophisticated, and the debate has not resolved. Researchers who entered this field expecting that better measurements would settle the question have instead watched the disagreement sharpen around methodological choices rather than close around a clean answer. The cold spot statistical status is, itself, an unsolved problem nested inside the larger unsolved problem of what physically produced it. What Lambda-CDM would need to fully accommodate the cold spot is some combination of rare fluctuation and extreme void producing an ISW signal strong enough to account for the observed temperature depression. The model can stretch to include both of those things happening together in the same small patch of sky. But asking how often that specific combination of circumstances occurs in a Lambda-CDM universe returns, again, to a probability estimate that makes cosmologists shift in their seats. The supervoid is there, the cold spot is there. They are aligned in direction, and yet the math connecting them, under the standard model, stubbornly refuses to fully close. A model that explains almost everything in the universe with extraordinary precision should not produce a feature like the cold spot without any good reason. But so far, it has not been able to avoid doing exactly that. Over the 2 decades since the cold spot turned up in the WMAP data, it has not suffered from a shortage of explanations. Cosmologists are not a group that tolerates an anomaly sitting in the open without taking a run at it. Since 2004, research groups on several continents have proposed mechanisms, built models, run simulations, published papers trying to account for what sits in that patch of Eridanus sky. Some of these explanations are technically sophisticated, some are elegant, and every single one of them has eventually come up short. One of the earliest serious candidates was something called a cosmic texture. To understand what that means, you have to go back to the first fractions of a second after the Big Bang, when the universe was cooling rapidly and fundamental forces were separating out from each other. During that cooling, the quantum fields that govern particle physics passed through phase transitions. In certain theoretical frameworks, those transitions could leave behind stable defects in the structure of space-time itself. Think of what happens when a material cools unevenly. Flaws form at the boundaries between regions that cooled at different rates. Textures are the cosmic equivalent of those flaws. They are knots or twists in quantum fields, carrying energy, moving through the universe, leaving marks on anything they pass through. When a texture unwinds, it releases energy in a pattern that would cool photons passing through that region in a specific, predictable way. A 2007 paper proposed that a single cosmic texture located in the direction of Eridanus could account for the cold spot's temperature profile almost exactly. The shape of the cold spot on the sky, the depth of the temperature dip, the spatial distribution of the cooling. All of it fit the texture model with uncomfortable precision. For a while, textures were a serious contender. Then the problems started. Textures of the size required to produce a cold spot this large should not be alone. They form throughout the universe during phase transitions. If one exists in Eridanus, the CMB should show signatures of others scattered across the sky. Planck's high-resolution data failed to find the broader population of texture signatures the model predicted. A single texture without a family of companions is not a prediction. It is an exception made for one anomaly. Physics rarely works that way. Textures quietly retreated from the front of the debate. What if the simplest answer is the right one? The cold spot could be nothing more than a statistical fluke. Standard cosmology generates a random distribution of temperature fluctuations across the CMB. In any random distribution, extreme values appear somewhere. The question is not whether cold regions exist, but whether a region this cold and this large was likely to show up in one particular sky. Researchers have run millions of simulated universes based on Lambda-CDM parameters, generated artificial CMB maps from those simulations, counted how often a feature as extreme as the cold spot appears. The results vary depending on how you define extreme and how you measure the statistics. Some analyses put the probability somewhere around 1 in 50, others using different filters or diff, errant measures of deviation. Push that number down to 1 in several hundred or even 1 in several thousand. That range is itself a problem. When your statistical significance depends heavily on which test you choose, you are not working with a clean result. Even at 1 in 50 though, the fluke explanation has a fundamental weakness that goes beyond the numbers. It is technically valid. It is not satisfying. Saying that the cold spot is an outlier within the model explains nothing about why it is there. It is the scientific equivalent of shrugging. When a feature survives 20 years of scrutiny and continues to resist physical explanation, calling it bad luck starts to feel less like an answer and more like giving up. Other proposals have circulated through the literature over the years, most of them less prominent but worth acknowledging. Some researchers proposed that foreground contamination from our own galaxy was distorting the signal in that direction. That dust or gas between us and the CMB was artificially suppressing the measured temperature. Careful multi-frequency analysis using Planck data was able to isolate the CMB signal from galactic foregrounds with high confidence. The cold spot remained. It was not an artifact of our galaxy leaking into the measurement. Others looked at whether secondary anisotropies, effects introduced by large-scale structure on photons after the CMB was released, could conspire to produce such a deep temperature minimum. The numbers never worked cleanly. Some papers proposed that the cold spot reflected unusual primordial conditions. A region of the early universe where the density fluctuations seeded by inflation was simply different from the average, a rare draw from the inflationary probability distribution. This is a version of the statistical fluke argument dressed in different language. It carries the same weakness. It identifies where the anomaly sits in the distribution without explaining what produced it. There were proposals involving modified initial conditions for inflation, unusual topological properties of the universe at the largest scales, even suggestions that the universe might be finite rather than infinite in a way that would generate unexpected correlations at large angular scales. Each of these ideas addressed one feature of the cold spot while struggling with others. None of them produced a comprehensive explanation that accounted for the temperature depth, the spatial scale, the shape, the absence of similar features elsewhere all at once. The cold spot is remarkably good at surviving contact with explanations. Each theory had its moment. Each eventually broke down under closer inspection, leaving the cold spot exactly where it started, unexplained. There is one explanation for the cold spot that has never quite gone away, no matter how many times mainstream cosmologists try to set it aside. Every other theory eventually faded. Textures were ruled out. Statistical flukes felt unsatisfying. The supervoid explained a fraction of the temperature depression and stopped there. And into that remaining gap, quietly and persistently, one idea kept returning. What if the cold spot is a scar left by another universe? This is not a fringe idea in the sense of being ignored. It has appeared in peer-reviewed papers. It has been taken seriously enough to model, to test against the data, to argue about in conference rooms. The hypothesis goes by several names, but the core claim is the same. Our universe is not the only one. It never was. And at some point in the distant past, something brushed against us. To understand how this works, you have to understand what inflationary cosmology actually predicts. In the first fraction of a second after the Big Bang, the universe underwent a period of explosive expansion called inflation. Space stretched faster than light can travel, smoothing out irregularities and seeding the density fluctuations that would eventually become galaxies. The theory of inflation is extraordinarily successful. It explains the flatness of the universe, the uniformity of the CMB, and the pattern of temperature fluctuations that satellites like WMAP and Planck have mapped in such precise detail. But inflation has a consequence that many physicists find uncomfortable. Once it starts, it does not stop everywhere at once. Different regions of space drop out of the inflationary state at different times. Regions that stop inflating become universes like ours. Regions that keep inflating keep producing new pockets, new bubbles of space that each expand into their own universe. This process is called eternal inflation. And in this picture, our universe is one bubble in a vast, possibly infinite sea of other bubbles. Each one is causally isolated from the others. Each one expands on its own. Most of them can never communicate with us in any way. Most, but not necessarily all. In some models, two bubble universes can come into contact. Not collide in the conventional sense of two objects slamming together, but touch at their boundaries as their expanding edges meet. If that happened, the collision would send a shockwave through the interior of each bubble. In our universe, that shockwave would propagate outward from the point of contact, affecting the temperature and density of matter and radiation in a ring-shaped region on the sky. From our vantage point, billions of years later, we would see the imprint as a disc-shaped anomaly in the CMB, cold or hot depending on the geometry, circular in shape, positioned wherever in the sky our bubble happened to make contact with its neighbor. Now look at the cold spot. It is roughly circular. It is anomalously cold. It sits in a well-defined region of sky, with an internal structure showing a colder core surrounded by a warmer ring. Some researchers noted that this profile is at least qualitatively consistent with what a bubble collision signature might look like. That observation was enough to keep the hypothesis alive, even as the majority of the field stayed skeptical. The skepticism is substantial, and it is not unreasonable. The most immediate problem is testability. A multiverse by construction lies beyond the boundary of our observable universe. We cannot send a probe there. We cannot observe the other bubbles directly. We cannot run an experiment that distinguishes a universe with bubble neighbors from one without them. Any theory that explains a single anomaly while being structurally immune to broader testing sits in uncomfortable scientific territory. Extraordinary claims require extraordinary evidence, and the cold spot alone does not come close to meeting that threshold. There is also the question of what, specifically, the prediction is. Different models of bubble collisions produce different signatures. Some predict a hot ring, some predict a cold disk, some predict asymmetric features. The parameter space is large enough that critics argue the hypothesis is not making a precise prediction so much as finding a way to fit whatever anomaly exists. A theory that can explain anything explains nothing. When researchers ran rigorous statistical comparisons between the cold spot's actual profile and the expected profile from bubble collision models, the match was imperfect, suggestive in some framings, unconvincing in others. The strongest version of the skeptical position is this: the cold spot has a mundane candidate explanation in the form of the Eridanus Supervoid. The supervoid is real, confirmed by independent surveys, and physically connected to the cold spot through a well-understood mechanism. The fact that the supervoid only explains 10 to 20% of the temperature depression is a serious problem, but that problem points toward incomplete physics or incomplete data, not necessarily toward a second universe. Invoking the multiverse to fill the remaining gap is to most cosmologists like explaining a crack in the sidewalk by proposing that tectonic plates exist without first checking whether someone dropped something heavy. And yet, the hypothesis has not been ruled out. No measurement has returned a result that definitively excludes bubble collision models. The cold spot's circular structure, its temperature profile, its position, none of these features are incompatible with an inflationary collision signature. They are also not incompatible with a supervoid plus a statistical fluctuation. But that is different from disproving the multiverse interpretation. The absence of disproof is not evidence. But in a field where the most exotic option remains technically consistent with every observation, technically consistent is enough to keep people writing papers. What does it say about the state of the problem that this explanation keeps resurfacing? It says that 2 decades of work by some of the most careful observers and theorists in cosmology have not produced a clean answer. The supervoid is real. The ISW effect is real. The math has been done. And still the bulk of the cold spot's temperature depression sits there, unaccounted for, waiting. When nothing in the standard toolkit closes the gap, people reach for tools that are further out. The multiverse hypothesis is the furthest tool on the shelf, the one that requires the most assumptions and offers the least direct testability. But it is on the shelf for a reason. The universe presented us with something that keeps resisting ordinary explanations. And physicists do not like loose ends. The multiverse hypothesis is still alive, not because the evidence demands it, but because nothing else has fully closed the case. Set aside the cold spot for a moment, and the Eridanus Supervoid has a second reason to command scientific attention. The mystery of the cold spot brought astronomers to this region of sky. But what they found there turns out to be useful for something far larger than one anomaly in one microwave map. The supervoid is a laboratory, and what it is testing is the most poorly understood force in the universe. To understand why, you have to understand what dark energy actually is. Or rather, what we know it does, since nobody has explained what it actually is. In 1998, 2 independent teams of astronomers measuring the distances to distant supernovae made the same discovery at nearly the same time. The universe was not just expanding, it was accelerating. Something was pushing space itself outward at an increasing rate, working against gravity on the largest scales, and that something had no name in any existing theory. They called it dark energy. It now accounts for roughly 68% of everything in the universe by energy content, and we have no idea what it is. What we do know is that dark energy dominates on the largest scales. Where gravity pulls matter together into clusters and filaments, dark energy operates in the spaces between, driving regions of low density to expand faster than regions with more matter. This distinction matters. In dense regions, galaxy clusters, filaments, the bright nodes of the cosmic web, gravity is running the show. But in voids, the story is different. Voids are regions where gravity lost. Matter drained away into the surrounding structure billions of years ago, and what was left behind is a region dominated not by gravitational collapse, but by the expansion of space itself. Dark energy is in charge in a void, and that makes voids the ideal place to measure it. This is the key insight. A supervoid is not just an absence of matter, it is a region where the physics of expansion is essentially running unopposed. The rate at which a void grows over time, the depth of the underdensity it develops, the precise shape of its density profile from center to edge, all of these are determined by the balance between gravity trying to pull matter back in and dark energy pushing the expansion outward. Change the properties of dark energy, and voids change with it. Change the equation of state of dark energy, the ratio that describes how its pressure relates to its density, and the void population across the universe shifts in measurable ways. Supervoids are, in a very real sense, tuning forks for dark energy. The Integrated Sachs-Wolfe effect comes back in here. The strength of the ISW signal produced by a supervoid depends directly on how dark energy behaves. In a universe without dark energy, photons passing through a void would lose energy climbing out of the gravitational hill, but the hill itself would not change during the crossing, and the photon would recover most of what it lost. Dark energy changes this. It stretches the void while the photon is still inside it. The hill the photon descends on the far side is shallower than the hill it climbed on the near side. The photon arrives slightly colder. The colder the signature, the stronger the dark energy signal imprinted on the crossing. Measure the ISW effect across enough supervoids, and you are directly measuring how aggressively dark energy is reshaping space. This is not theoretical speculation. The Dark Energy Survey was built precisely to gather the kind of galaxy data needed to find and characterize supervoids at cosmological distances, and the Eridanus Supervoid is the most prominent structure it found. The DES measurements confirmed not just the supervoid's existence, but its density profile, how the underdensity deepens toward the center, how it falls off at the edges, how its elongated shape relates to the matter flows that emptied it. These are not decorative details. Each one constrains the cosmological model. Each one puts a slightly tighter boundary on what dark energy can and cannot be doing on these scales. The constraints that supervoids provide are complementary to the constraints from other dark energy probes. Type 1a supernovae measure the expansion history of the universe by tracking how the brightness of standard candles changes with distance. Baryon acoustic oscillations measure the scale of the cosmic web by looking for a characteristic spacing in galaxy distributions. The CMB itself constrains the early universe's composition. Supervoids add something different. They probe dark energy's influence on structure growth. Not just how fast the universe is expanding, but how that expansion is shaping the largest underdense regions over cosmic time. Different probes can give the same answer for some dark energy models while disagreeing sharply for others. Supervoids help break those degeneracies. There is a specific number that cosmologists track when they try to characterize dark energy. It is called W, the equation of state parameter. In the simplest model, the cosmological constant, the lambda in Lambda-CDM, W equals -1 exactly, permanently, everywhere. In more complicated models, W could vary with time or differ from -1 in ways that would change the history of cosmic acceleration. The growth rate of supervoids is sensitive to W. A universe with a different value of W would produce supervoids with different typical sizes, different depth profiles, and different ISW signatures. The Eridanus Supervoid alone cannot pin down W with the precision needed to distinguish between models. But a population of supervoids measured across the full DES survey, combined with data from galaxy lensing and CMB observations, can push those constraints considerably further. That work is ongoing. What sits underneath all of this is the possibility that the cold spot, even if it turns out to be explainable within the standard model, has pointed astronomers toward a tool they would have spent decades looking for. The supervoid revealed by the search for the cold spot's cause is now one of the most valuable dark energy laboratories available. That is an unlikely outcome for what began as a strange smudge on a microwave map. Whatever answer eventually emerges from the supervoid data, it will have something to say about the force that is tearing the universe apart. Once the cold spot had a name, astronomers started looking for others. That impulse is not unusual. When any anomaly survives early scrutiny, the natural next move is to ask whether it is truly singular or whether the universe has been producing similar features all along and nobody was looking carefully enough to notice. The cold spot had survived scrutiny. It had survived multiple instrument checks, multiple statistical analyses, multiple attempts to attribute it to foreground contamination or noise. So in the years after the WMAP discovery, groups of researchers turned their attention outward, combing through the data for other cold regions that might share the same character. In 2009, a team of astronomers in Australia conducted one of the most comprehensive surveys of the southern sky undertaken at that point. They mapped roughly 41% of the southern hemisphere, cataloguing hundreds of candidate voids distributed across enormous stretches of sky. The sheer number of candidates was, at first, striking. Hundreds of potential underdensities, each one a place where galaxies were thinner on the ground than the cosmic average. What it suggested was something cosmologists had suspected but not fully confirmed, that voids were not rare curiosities scattered through an otherwise uniform universe. They were everywhere. The cosmic web, it turned out, was made as much of emptiness as of structure. That emptiness was distributed across the sky in patterns that had never been fully mapped. But quantity was not the same as equivalence. Most of the candidate voids found in that survey were small, shallow, unremarkable by the standards of the Eridanus structure. They were the ordinary furniture of a universe organized around filaments and walls. A handful were genuinely large. None matched the Eridanus Supervoid in scale or depth. The survey expanded the inventory of known underdense regions, but it did not immediately produce a second Eridanus. Then came a more unsettling development. Researchers working through the WMAP data began reporting that the original cold spot might not be the only thermal anomaly worth tracking. There appeared to be cold features in the northern hemisphere of the CMB as well. Not a single sharp counterpart, but a pattern of cooler-than-average regions distributed in ways that did not match simple statistical expectation. Some teams described this as a general asymmetry between the northern and southern hemispheres of the CMB map, with the southern hemisphere running slightly cooler on average. Others were more cautious, pointing out that the statistical tests being applied were sensitive to the choices researchers made when designing them. What this opened was a harder question than the one the cold spot had originally posed. If the anomaly was not a single point but a broader pattern, then the explanation could not simply be a single supervoid sitting in the right place. A supervoid could explain one cold spot. It could not explain a hemisphere, something about the large-scale structure of the universe, or something about the CMB itself might be producing cold features more systematically than the standard model predicted. Were supervoids everywhere, draining energy from CMB photons at a rate that standard simulations consistently underestimated? Was the Integrated Sachs-Wolfe effect stronger in reality than the models suggested? These were not comfortable questions. This was because answering them would require confronting the possibility that the standard cosmological picture had a systematic flaw, not just a single outlier. The Planck satellite, which launched in 2009 and began releasing data in the following years, gave researchers their first genuinely high-resolution look at the cold spot's internal structure. What Planck showed was that the cold region was not featureless. It had a colder core surrounded by a ring of slightly warmer temperatures, a profile that did not obviously match the smooth, gradual imprint expected from a supervoid acting through the ISW effect alone. Some researchers argued that the internal structure was consistent with a more complex void geometry. Others saw it as evidence that something additional was going on, that the supervoid and the CMB feature were related, but not simply caused by one another in the straightforward way the original hypothesis had implied. Planck also confirmed what WMAP had shown, which mattered more than it might sound. Instruments fail. Calibrations drift. Foreground signals from our own galaxy can masquerade as cosmological features. Every time a new instrument with different systematics looked at the cold spot and saw the same thing. The probability that the whole thing was an artifact dropped closer to zero. By the time Planck's full data releases were complete, the cold spot had been confirmed by two independent satellites operating on different principles. The confirmation was not marginal. The feature was there. It was cold. It was large. And its internal structure was real. What the search for other cold spots ultimately produced was not a clean resolution. It produced a harder version of the original problem. The universe appeared to contain more large underdensities than the standard model comfortably predicted. CMB cold features appeared in more than one location, though none with the combined size and depth of the Eridanus anomaly. The Eridanus cold spot remained in a class of its own, but it was no longer easy to treat it as a completely isolated freak of cosmic statistics. It was beginning to look like the most extreme example of a phenomenon the models were consistently getting wrong. Whether that was a problem with the models or simply the expected behavior of a universe large enough to contain genuine outliers was a debate the data had not yet settled. The question was no longer whether the cold spot was real, but whether it was alone. When the European Space Agency launched the Planck satellite in 2009, the cold spot was one of the anomalies it was specifically equipped to study. WMAP had done something remarkable. It had given astronomers their first detailed portrait of the microwave sky. But Planck was a different instrument entirely. Where WMAP had angular resolution of about 13 arc-minutes at best, Planck pushed that to 5 arc-minutes. That is not a modest improvement. It is the difference between a photograph taken through a fogged window and one taken with a precision lens in clean air. You are not looking at the same image. Planck also carried something WMAP could not match: 9 frequency channels spanning a range from 30 to 857 GHz. This matters because the CMB is not the only thing emitting microwave radiation across the sky. Our own galaxy leaks signal into every map: dust, free electrons, synchrotron radiation from charged particles spiraling through magnetic fields. All of it sits between us and the ancient light we are trying to read. Separating the genuine CMB signal from that foreground contamination requires comparing measurements at different frequencies, since each source has a different spectral signature. WMAP had 5 frequency channels, Planck had 9. That extra coverage let researchers scrub the foreground contamination far more cleanly than had been possible before. What was left behind was a map of the CMB that was sharper, colder, and more honest than anything that had come before it. When Planck's team turned that cleaned map toward the cold spot, what they found was not simpler, it was stranger. The cold region was not a uniform patch of depressed temperature, it had structure. At its center sat a core noticeably colder than the surrounding area. Around that core was a ring, warmer than the core, but still colder than the CMB average. Around the ring was another zone, slightly warmer relative to the average in the surrounding sky. This was not a smooth, featureless dip in the data. It was layered, concentric, almost architectural. Whatever had produced it had not produced it uniformly, and that internal structure carried information. Exactly what information was the parts that divided researchers? Different teams looked at the same Planck data and reached different numbers. Some groups ran statistical tests that placed the cold spot at roughly a 1 in 50 probability of occurring by chance within a standard cosmological model. Others applied different methods to the same dataset and arrived at odds closer to 1 in several hundred, or even rarer still. The fact that the range was this wide was not a sign of sloppiness. It was a sign of genuine statistical difficulty. The cold spot sits at the edge of where the standard tools start to disagree with each other. One group would define the anomaly using a specific filter and a specific measure of coldness. Another group would apply a slightly different filter, a slightly different measure, and get a number that looked meaningfully different. Both teams were being rigorous. They were just asking slightly different questions, and the cold spot was answering them differently. This kind of disagreement sounds like uncertainty, and it is. But there is a signal buried inside the disagreement. No matter which method was applied, no matter which team ran the numbers, no team found the cold spot to be statistically unremarkable. The floor of improbability never dropped below 1 in several dozen, even in the most conservative analyses. The cold spot was always sitting at the edge of what the standard model would comfortably produce, regardless of exactly how you drew the boundary. That persistent discomfort, across years and teams and methods, is what the Planck era gave the field as a kind of consensus. Planck also refined what researchers knew about the Eridanus Supervoid itself. When the Planck CMB maps were combined with the galaxy distribution surveys being assembled at the same time, it became possible to study the relationship between the supervoid structure and the cold spot's temperature profile in far more detail than before. The colder core of the cold spot appeared to correspond with the deepest part of the void, the region of most extreme underdensity near the center, where the matter deficit was most severe. The surrounding ring of slightly less extreme temperature depression matched a region of less extreme underdensity toward the void's outer boundary. The correspondence was not perfect, and researchers argued about exactly how much of that alignment was meaningful versus coincidental. But the shapes were talking to each other in a way that older, lower resolution data had not revealed clearly. What Planck could not do was close the case. The temperature measurements it produced were precise enough to sharpen the question considerably, but sharpening the question only made the gap between the supervoid's predicted ISW effect and the observed temperature depression look more stark. A cruder instrument can leave room for error to hide in. Planck removed much of that room. The discrepancy between what the supervoid should produce and what the cold spot actually shows did not shrink when Planck arrived. If anything, the improved data made it harder to wave away. Planck did not solve the cold spot, but it made absolutely certain that the cold spot was real. After 2 decades of observation, analysis and argument, the honest summary of what we know about the cold spot is shorter than it should be. The Eridanus Supervoid is real. The cold spot is real. They occupy the same patch of sky. Those 3 facts are settled. Everything else, why the temperatures are what they are, whether one caused the other, what fills the gap between the physics and the observations, remains genuinely open, not almost solved, not close, open. Start with the number that should bother you. The Integrated Sachs-Wolfe effect, acting through the supervoid, can account for somewhere between 10 and 20% of the cold spot's observed temperature depression. That is the best case estimate under the standard cosmological model. It means that after finding the largest identified void in the observable universe sitting directly behind the most anomalous feature in the CMB, after confirming that void through 2 independent observational methods, after 2 decades of increasingly precise measurements, the physics still leaves 80 to 90% of the temperature signal unexplained. The supervoid is real, the supervoid is enormous, and the supervoid is not enough. Andrus Kovacs, the lead researcher on one of the most comprehensive recent studies of the region, put it carefully. Having 2 individually rare structures coincide in the same direction, he said, is not sufficient to prove causality by the standard science demands. That is a precise and honest statement, and it deserves to sit in your mind for a moment. Spatial coincidence is suggestive, it is compelling, it keeps researchers working. But coincidence is not causality, and in a field where the margins between a real signal and a statistical artifact have enormous consequences, the distinction matters. The case has not been made to the standard the physics requires. The internal structure of the supervoid adds another layer of uncertainty. What researchers have measured so far is a broad brush picture, a region roughly 1.8 billion light-years across, containing approximately 30% less matter than the cosmic average, elongated along certain axes. But a void of that scale almost certainly contains subvoids nested inside it, denser filaments threading through its interior. Pockets of varying underdensity that the current galaxy surveys do not resolve clearly enough to map. The density profile, how sharply the underdensity deepens toward the center, how it fades at the edges, is constrained but not fully characterized. That profile matters because the ISW temperature signal depends directly on how the gravitational potential changes as a photon passes through. A different density profile produces a different temperature imprint. Without a precise three-dimensional map of the supervoid's interior, researchers are working with an approximation, and approximations compound. The role of dark matter inside the void is similarly incomplete. The 2015 Dark Energy Survey results confirmed a dark matter underdensity in the same region as the galaxy underdensity. That confirmation was significant, but knowing that dark matter is underrepresented in that region is different from knowing by exactly how much and in exactly what distribution. Dark matter cannot be observed directly. Its presence is inferred through gravitational effects on light and on the motions of galaxies. In a region specifically defined by having very few galaxies, those inferences carry larger uncertainties than they would anywhere else. The very emptiness that makes the supervoid scientifically interesting also makes it harder to measure with precision. Then there is the statistical question, and this one has not settled down despite years of argument. Is the cold spot a genuine anomaly? Something that the Lambda-CDM model cannot produce with any reasonable probability? Or is it an extreme but legitimate fluctuation that the model technically allows? Different research groups, applying different statistical frameworks to the same Planck data, have reached conclusions ranging from roughly 1 in 50 to roughly 1 in several thousand. That spread is not a sign that one team made an error. It reflects genuine disagreement about how to count, what to compare, and how to define the feature being tested. The cold spot has a colder core and a surrounding ring, which makes defining its boundaries a choice rather than a measurement. Statistics run n different boundary choices produce different significance values. The answer you get depends partly on how you ask the question, and no consensus has emerged on how to ask it correctly. What about similar configurations elsewhere? If the cold spot is caused by a supervoid through the ISW effect, then similar supervoids in similar positions along other lines of sight should produce similar cold signatures. Researchers have looked. The 2009 survey of the southern sky found hundreds of candidate voids. Some CMB surveys have found other cold regions, but none of them combine the extreme temperature depression and the extreme underdensity of the Eridanus case at the same level of significance. Whether that means the Eridanus case is genuinely unique, or whether it means the surveys have not yet found its counterparts, is not known. A universe filled with undetected supervoids producing undetected cold signatures would look exactly like a universe where the cold spot is a 1T ion event, at least with the tools currently available. This is the position the field is in. Not stuck, exactly. New data keeps arriving, new methods keep developing, new constraints keep tightening around the problem, but not close to resolved either. The supervoid explains a fraction of what needs explaining. The causal link between the void and the cold spot is strongly suggested and not proven. The void's internal structure is partially mapped. The dark matter distribution inside it is constrained but not characterized. The statistical significance of the cold spot is disputed. And whether the standard model is genuinely incomplete or simply being tested at its extreme edge remains the central question with no definitive answer. The gap between what the supervoid can explain and what the cold spot actually shows has not closed. If anything, better measurements have made it look wider. There is a patch of sky in the constellation Eridanus that is, in a specific and meaningful sense, the coldest place we can observe in the universe. That sentence requires some unpacking, because the coldness here is not the kind your instruments would measure if you flew a spacecraft into that region and checked the temperature of the gas. It is not cold the way deep space between galaxies is cold. The supervoid contains matter. It contains galaxies, gas clouds, the occasional cluster of stars. Whatever matter exists inside that void has temperatures comparable to anything else at similar scales in the universe. The coldness is not in the void itself. It is in the light that passed through it. What makes the Eridanus region the coldest observable feature in the universe is strictly this. The photons arriving from that direction carry less energy than photons arriving from nearly any other comparable patch of sky. The cosmic microwave background radiation streaming toward us from the Eridanus direction has been slightly depleted. It has climbed a gravitational hill, and the expansion of the universe stretched that hill while the photons were crossing it, so they could not recover what they lost on the way up. The result is radiation that reads cold. Not physically cold in any local sense. Cold in the most observational sense possible. Radiation arriving at our detectors with a deficit of energy that measures roughly 70 microkelvin below the average temperature of the CMB. That number sounds trivial. It is not. The average temperature of the CMB is 2.725 Kelvin, barely above absolute zero already. The typical fluctuations that seed galaxies, that carry the entire history of structure formation in the universe, run about 18 microkelvin above or below the mean. The cold spot sits at 70 microkelvin below. It is not a whisper outside the normal range. It is a shout. So what does it actually look like inside the region producing this? Imagine the cosmic web as it exists across billions of light years. Filaments of dark matter and ordinary matter stretching between nodes. Dense clusters where matter has pooled over billions of years of gravitational attraction. And between those structures, voids, regions where matter drained away, following the pull of denser neighborhoods, leaving behind something closer to genuine emptiness than almost anywhere else in the universe. The Eridanus Supervoid is one of these regions scaled up to a size that strains comprehension, roughly 1.8 billion light-years across, containing perhaps 30% less matter than the cosmic average. Toward its center, even less. Galaxy formation did not proceed efficiently here. That is not a metaphor for something subtle. In the densest regions of the universe, galaxies form because matter pulls on matter. Overdense patches attract more material. Dark matter halos grow. Gas falls in, cools, collapses, ignites into stars. The process feeds itself. In an underdense region, the opposite dynamic dominates. Matter that might have collapsed was pulled away toward denser surroundings before it could accumulate. The few galaxies that did form inside the supervoid are sparse and isolated, scattered across a volume so enormous that the distances between them dwarf the distances in more typical regions of the cosmic web. If you were inside the supervoid and could somehow see the structure around you, the sky would be darker. The filaments visible in denser parts of the universe simply would not be there. The cosmic web in that region stretched thin over billions of years. The large-scale gravitational environment around the supervoid has been draining matter from its interior across most of cosmic history. Dark energy accelerates this process by expanding space itself, pulling the void's walls apart, deepening the underdensity, extending the gravitational hill that CMB photons must cross when they travel in our direction from behind it. What you are looking at in the Eridanus direction is not an event. It is a slow process, running across billions of years, that has produced the single largest and deepest departure from the average texture of the universe that we have identified anywhere in the observable sky. There is something worth sitting with here. When you look at the full sky CMB map, that oval image you have probably seen, the ancient light of the universe displayed in false color, the cold spot is visible. A blue region in the lower half of the map, slightly more prominent than its surroundings, representing the oldest and coldest signal in the portrait of the early universe. What produced that feature was not present in the early universe. The supervoid did not exist 380,000 years after the Big Bang, when that light was released. It formed later, as structure grew, as matter flowed and clustered, and left certain regions behind. The cold imprint on that ancient map is a late addition, a signature written onto the oldest light in the universe by something that came afterward. That is a strange thing to hold in your mind. The CMB is a snapshot of the universe in its infancy, but the cold spot is not a feature of that infancy. It is a shadow cast by something that grew up long after the snapshot was taken, a supervoid that imprinted itself onto ancient light as that light crossed through it on its way to us. What we see as a feature of the early universe is partly a product of something billions of years more recent. You could point a telescope at the center of the Eridanus Supervoid and find galaxies, fewer than elsewhere, spread across distances that reflect the thinness of structure in that region. Nothing about those galaxies, looked at directly, tells you they are sitting inside the coldest observable feature in the universe. The coldness is not a property of anything physical inside the void. It is a property of what happened to light passing through. It is not cold because something chilled it. It is cold because something was never there. The next generation of observational tools is not going to leave the cold spot alone. For 2 decades, the mystery has outpaced the instruments chasing it. That is about to change. Several of the most ambitious observational projects in the history of cosmology are now either operational or approaching first light. A significant portion of their scientific programs point directly at the question of what is happening in the Eridanus region. The cold spot has been waiting. The instruments have finally caught up. The Rubin Observatory, sitting at 8,000 feet in the Chilean Andes, is preparing to begin its legacy survey of space and time. LSST will photograph the entire southern sky repeatedly over 10 years, building a catalogue of roughly 20 billion galaxies. 20 billion. The Eridanus Supervoid sits in the southern hemisphere. LSST will pass over that region of sky thousands of times during its survey lifetime. What this means in practice is a galaxy map of the cold spot region with a depth and precision that no previous instrument has come close to matching. Researchers will be able to trace the distribution of galaxies, not just in projection on the sky, but in 3 dimensions, mapping how the density changes as you move along the line of sight through and beyond the supervoid. The question of where exactly the underdensity begins, where it deepens, where it fades back into the surrounding cosmic web, will finally have a precise answer. At the same time, the Euclid satellite is already in space. The European Space Agency launched it in 2023. Its mission is mapping the 3-dimensional distribution of galaxies across more than 1/3 of the entire sky, with extraordinary resolution. Euclid is specifically designed to study dark energy and large-scale structure. That makes the Eridanus Supervoid essentially a primary target. The satellite measures galaxy shapes with enough precision to detect weak gravitational lensing signals from structures at cosmological distances. That is the same lensing technique that helped confirm the supervoid's dark matter underdensity in 2015, only now applied with sensitivity several times greater. If there is structure inside the supervoid that earlier surveys missed, subvoids, filaments of residual matter, gradients in the density profile, Euclid has a realistic chance of finding it. The 3-dimensional picture Euclid and LSST will build together, combined with existing data from the Dark Energy Survey, will be far more complete than anything the field currently has to work with. The CMB side of the problem is also moving forward. Ground-based experiments like the Simons Observatory in Chile and the planned CMB-S4 experiment will reach sensitivities in CMB temperature and polarization measurements that would have seemed implausible a decade ago. CMB-S4 alone is designed to produce a map of the microwave sky roughly 7 times more sensitive than Planck's final data release. What that sensitivity buys you, in practical terms, is the ability to detect the integrated Sachs-Wolfe signal from individual large structures, rather than just stacking statistical averages across many voids. Right now, the ISW signal from the Eridanus Supervoid cannot be cleanly isolated against the noise in existing CMB maps. It is too faint relative to the instrument's sensitivity. With CMB-S4 data, that calculation changes. Researchers may be able to directly measure how much the supervoid has cooled the photons passing through it. Compare that number to what the standard model predicts. If the numbers match, the standard picture survives. If they do not, the discrepancy will be sitting in high-quality data that no one can argue away. There is another piece of the puzzle that better data will sharpen: neutrino mass. Neutrinos are extraordinarily light particles that fill the universe in enormous numbers. Their mass, still only loosely constrained, affects how structure forms on large scales. Massive neutrinos suppress the growth of cosmic structure at certain scales. That changes the predicted depth and evolution of voids. Current uncertainty in neutrino mass is large enough that it introduces meaningful uncertainty into predictions about supervoid properties. The next generation of cosmological surveys, including Euclid and LSST, will constrain neutrino mass to a level of precision that closes this loophole. Models of how the Eridanus Supervoid formed and deepened over cosmic time will become correspondingly sharper, either tightening the agreement with Lambda-CDM or making the tension harder to dismiss. What researchers are building toward is something that has never existed before: a complete, high-resolution, three-dimensional picture of the matter distribution in the Eridanus direction, a precise CMB temperature profile of the cold spot, including its internal structure, a direct observational measurement of the ISW signal from the supervoid, all within the same decade. Put those three things together and you have a system of constraints tight enough to actually test whether the standard model can accommodate what is observed. The cold spot has survived for 20 years in part because the data was never quite complete enough to close the argument. That situation is ending. The instruments being built right now will be pointed at Eridanus within the decade. Whatever they find will not leave the standard cosmological picture unchanged. Every so often in the history of physics, an anomaly that could have been waved away as a statistical fluke turned out to be the fingerprint of something the existing theory had no room for. The perihelion of Mercury drifted slightly too fast for Newtonian gravity to explain. For decades it sat in the data, uncomfortable, officially unsolved. Then general relativity arrived and the drift made perfect sense. The ultraviolet catastrophe in classical thermodynamics seemed like a minor technical problem until Planck resolved it with quantum mechanics and changed everything. Anomalies like these are not just curiosities, they are the seams in a theory, the places where something underneath is trying to show through. The cold spot might be one of those seams, or it might not be. That uncertainty is itself the story. Lambda-CDM is not a narrow theory about one patch of sky. It is the structural foundation of modern cosmology. Every model of how galaxies formed, every calculation of how dark matter clumped in the early universe, every prediction about the geometry of space and the ultimate fate of everything in it, all of that rests on Lambda-CDM. When the model works, it works extraordinarily well. It predicted the acoustic peaks in the CMB before satellites confirmed them. It correctly describes the large-scale distribution of galaxies across billions of light years. It accounts for the expansion history of the universe with remarkable precision. A theory with that kind of track record does not get abandoned lightly. It should not be. But track records do not make theories immune to failure. And if the cold spot genuinely cannot be accommodated within Lambda-CDM, If better data and sharper analysis confirm that the temperature depression is too extreme, too large, and too structured to be a statistical accident, then the model has a problem. Not a footnote problem, a foundational problem. What would that actually require? What kinds of new physics could step in where Lambda-CDM falls short? One class of proposals involves modifying how gravity behaves on the larger scales. General relativity is the gravitational theory embedded inside Lambda-CDM, and it has been tested with extraordinary precision within the solar system and in the strong field regime around neutron stars and black holes. But cosmic scales are different. The behavior of gravity on scales of hundreds of megaparsecs has not been tested with the same rigor. Modified gravity theories, frameworks like FR gravity, or theories with additional scalar fields can change the way large-scale structure forms and the way voids evolve. Some of these models predict deeper, faster-growing voids than standard Lambda-CDM does. A supervoid in a modified gravity universe could in principle produce a stronger ISW imprint on T, CMB, potentially accounting for more of the cold spot's temperature depression than the standard model allows. Whether the numbers actually work depends on which modification you choose and what the observations constrain. So far, no specific modified gravity model has cleanly solved the cold spot problem, but the possibility remains open. A second direction involves dark energy. Lambda-CDM treats dark energy as a cosmological constant, a fixed uniform energy density filling all of space, characterized by a single number. Real dark energy might be more complicated than that. If dark energy varies across space or changes with time, it would alter the rate at which voids grow and deepen, and it would change the magnitude of the ISW effect. A dark energy equation of state, different from the standard value, could, depending on the direction of the deviation, either amplify or suppress the cold spot signal. Supervoids like Eridanus are particularly sensitive to this because void growth is driven almost entirely by cosmic expansion rather than local gravitational dynamics. The Eridanus Supervoid's measured properties, combined with the strength of the cold spot, place constraints on what dark energy can be doing. And some analyses suggest those constraints are already pushing against the edges of what Lambda-CDM comfortably predicts. There are stranger proposals. Some researchers have explored whether the cold spot could reflect an anisotropy in the universe itself, a preferred direction in space, which Lambda-CDM explicitly forbids. A universe that is not perfectly isotropic on the largest scales would violate one of the foundational assumptions of the standard model. If the cold spot is part of a broader pattern of large-scale anisotropy, that would be a significantly more serious challenge than a single anomalous temperature measurement. Evidence for this remains weak and contested, but the possibility has not been ruled out. Here is what makes all of this difficult to resolve quickly. To distinguish between Lambda-CDM and its competitors, you need measurements precise enough to detect differences that are genuinely small. Small in terms of the equation of state of dark energy, small in terms of how void growth rates deviate from standard predictions. The gap between what current instruments can measure and what you would need to definitively settle these questions is real. The next decade of surveys and experiments will narrow that gap considerably, but the answer is not here yet. What is here is the cold spot itself, sitting in the data, 70 microkelvin below average, spanning a region of sky that corresponds to one of the largest underdensities in the observable universe, partially explained and partially not. If it is a fluke, it is one of the most persistent and precisely characterized flukes in the history of observational science. If it is not a fluke, if the standard model genuinely has no room for it, then something beyond Lambda-CDM is operating at cosmic scales, and the cold spot is where we first noticed. Blind spots in successful theories are exactly where new physics has always lived. Mercury's drifting orbit looked minor. The ultraviolet catastrophe looked technical. Neither one was. The cold spot may be nothing more than a rare fluctuation in an otherwise well-behaved universe. Or it may be the place where the standard model of cosmology quietly runs out of answers. On a clear night in the southern hemisphere, the constellation Eridanus arcs low across the sky, a long winding river of dim stars named after a mythological waterway. It is not a dramatic constellation. No bright anchor star draws the eye the way Sirius does. No distinctive shape snaps into focus the way Orion does. Eridanus is faint, sprawling, easy to overlook. Most people who have spent years watching the southern sky have passed over it dozens of times without stopping. But there is a specific patch within it, unmarked and invisible, that has occupied some of the sharpest minds in cosmology for 20 years. You cannot see it. There is nothing there to see. That is precisely the point. If you were hovering in a spacecraft somewhere inside the Eridanus Supervoid, you would not know it. The void is not dark in the way a shadow is dark. There are galaxies inside it. Not many, perhaps 30% fewer than you would find in a comparable volume elsewhere. But they are there, burning the same way galaxies always burn, producing light indistinguishable from any other galaxy in any other corner of the universe. The void does not announce itself. It is defined by what is absent, not by what is present. Matter simply thinned out here billions of years ago, drawn away by the gravitational pull of denser surrounding regions, and the thinning never stopped. What remains is a region of space that is almost ordinary, except in aggregate, and at a scale no human eye could ever take in at once. The coldness you are dealing with is not a temperature you could feel. It is not the cold of deep space, where gas clouds drift at a few degrees above absolute zero. It is something stranger. The coldness exists in light, specifically in the photons of the cosmic microwave background that passed through this supervoid on their way to our detectors. Each photon climbed the gentle gravitational slope of the void, lost a small amount of energy doing it, and then came down the other side into a universe that had expanded just enough during that crossing that the energy could not be fully recovered. 70 microkelvin below the surrounding average. That is what the cold spot is. Not a cold place, but cold light. Light that arrived slightly depleted, carrying the faint record of a billion light-year crossing through near emptiness. What does it mean to look in that direction and know this? It changes something. The patch of sky you are looking at is not special in any way your eyes can register. The stars between here and Eridanus are ordinary stars at ordinary distances, completely unrelated to the supervoid behind them. The supervoid itself sits 1.9 billion light-years away. Nothing about it is visible, and yet the radiation coming from that direction has passed through the largest identified void in the observable universe, and arrived here carrying a temperature signature that 2 decades of cosmology have not been able to fully explain. That is the situation. You are looking at an explanation that is still missing most of its pieces. Here is what the science actually says, stated plainly. The supervoid is real. Multiple independent surveys confirmed it. The cold spot is real. Multiple satellites measured it. The supervoid sits in the right location to influence the cold spot through the Integrated Sachs-Wolfe effect, and that effect is real and physically well understood. But the supervoid can only account for somewhere between 10 and 20% of the observed temperature depression. The rest, the majority of what makes the cold spot anomalous, has no accepted explanation within the standard cosmological model. That gap has not closed. Better measurements have, if anything, made it look more stubborn. Whatever is producing the remainder of the cold spot is either something within our current theoretical framework that we have not accounted for correctly, or something outside it. Nobody knows which. Were we watching a patch of sky that carries evidence of a collision with another universe? Probably not. Is it a statistical accident, an outlier that the standard model technically permits at low probability? Possibly. Is it evidence of physics that the Lambda-CDM model does not contain? Maybe. The discomfort of this situation is that all three remain on the table, and the observations so far have not been precise enough to eliminate any of them with confidence. The instruments being built right now, the surveys coming online over the next decade, will map the matter distribution in that region at a resolution we have never had before. That data will close some of the possibilities. It may not close all of them. Find Eridanus on a clear southern night and hold that in your mind. The constellation itself is just a convenient label, a name we put on a region of sky so we can talk about it. The river of stars is not connected to the supervoid behind it in any physical way, but the direction is the direction. Somewhere along that line of sight, 1.9 billion light-years out, space grew thin, matter drained away. The cosmic web stretched to almost nothing in a region larger than most of the mind can honestly picture. And the ancient light of the early universe passed through it and came out the other side slightly depleted, arriving at our satellites carrying a temperature anomaly that we still cannot explain. 20 years of work on a single patch of sky, and the answer is still not there. The coldest spot in the observable universe looks like nothing at all from down here, which is perhaps the strangest thing about it.